And one last thing, AP Physics C students should be able to derive the equations for the period of a mass spring system, period of a simple pendulum, and period of a physical pendulum. Let's start with the mass spring system. A mass M is attached to a spring with spring constant K. The system is stretched, then released, causing it to oscillate in simple harmonic motion. Letter A says, write a second order differential equation using Newton's second law. Let's start with that. Since it says using Newton's second law, we're going to start by writing F equals ma. To turn that into a second order differential equation, all that means is that we have to write the acceleration as the second derivative of displacement with respect to time. And for F, the net force in an oscillating system of a mass on a spring is going to be equal to Hooke's law, negative kx. So this is our second order differential equation. All right, part B says derive the equation for the period of the mass spring system in terms of given variables and fundamental constants. So we're now going to take that second order differential equation, and I divided both sides by m. And I know that if something is in simple harmonic motion, that the general form for simple harmonic motion is that the second order derivative of the displacement with respect to time is equal to negative angular velocity squared times x. So I'm replacing this derivative here with negative omega squared x, and then just doing a little canceling. So I dropped the negatives and I dropped an x, and we get w squared or omega squared equals k over m. So now I'm going to take the square root of that. We also know that angular frequency is equal to 2 pi f, and f is 1 over t. So omega is also equal to 2 pi over t. So I put that down. So now all I have to do is do my algebra to solve for t, and we'll end up with t equals 2 pi square root of m over k. Next, let's look at the simple pendulum. It's a little bit more complicated. A simple pendulum of length L rotates about one end. Write a second order differential equation using Newton's second law in rotational form. So let's start with that. So we're going to start by writing Newton's second law in rotational form, which is T equals I alpha. And now to turn it into the second order differential equation, I'm going to write the acceleration in terms of the second derivative of the angular displacement with respect to time. And then I'll make another replacement over here. So torque is normally F times R. But in this case, we have a point mass. And the R value would be the distance from the point mass to the axis of rotation. So in this case, the R value is going to be equal to L. So I wrote that as negative FL. And we do know what the value for the force is, or we know that the restoring force is equal to mg sine theta for a simple pendulum. So I plugged that in for the force. So this now would be the second order differential equation using Newton's second law in rotational form. So now we're going to use this to do part B. Derive the equation for the period of the pendulum in terms of given variables and fundamental constants. So we're going to write that down. I divided both sides by I to move that to the other side. And I have here mg sine theta L divided by the rotational inertia. And now we are going to apply the small angle approximation. The small angle approximation is a simplification that says that the sine of theta is approximately equal to just theta as long as it's swinging at small amplitudes. So we'll accept that small amplitude consideration, and we can now replace sine theta with just theta. And so now just doing a little bit of algebra, we can cancel the m's. We can cancel one of the L's in the L in the numerator and one of them in the denominator, and I end up with negative G over L times theta. I should recognize that this is very close to the standard form for something that's oscillating in simple harmonic motion. So here we have the angular accelerations, here we have the negative sign, here we have the theta. So that tells me that G over L has to be equal to negative omega squared. So I'm going to take that and I'm going to write that over here. Omega squared is going to be equal to G over L because they're both in that same position in those standard form equations. So now we'll square root both sides, and we know that the angular frequency is equal to 2 pi f, which is equal to 2 pi 1 over t. And so I plugged in the 2 pi over t. And now I just did algebra to solve for t, and we end up with t equals 2 pi square root of L over G, which is our period of a simple pendulum equation. But we have to remember that because we applied the small angle approximation, that equation only holds true when it's swinging at small amplitudes. The derivation for the period of a physical pendulum is similar to that of a simple pendulum, but let's talk through it. A physical pendulum of mass m and length L rotates about one end. Write a second order differential equation using Newton's second law in rotational form. So let's start with that. So again, we're going to write down T equals I alpha. That's the second law in rotational form. And we're going to rewrite the angular acceleration as the second derivative of the angular displacement with respect to time. So now let's look at the torque. Torque is normally F times R or F times L. But when we think about a physical pendulum, we are thinking about all of its mass being concentrated at the center of mass. So the torque is going to be equal to F times D, where D is the location of the center of mass to the pivot point. And again, we know that the restoring force of a physical pendulum is equal to negative mg sine theta. So there's my second order differential equation, and we're going to use that for part B, where it says derive the equation for the period of the physical pendulum in terms of given variables and fundamental constants. So we're going to write this down, and the first thing I did is divide both sides by I, by the rotational inertia. So now we're going to apply the small angle approximation, where sine theta is approximately equal to just theta. And again, I'm just going to kind of rearrange the form here. So I switched the position of theta and d so that this equation could be written in the standard form of something that is in simple harmonic motion. So now I have the angular acceleration, I have the negative sign, I have the theta, and so that tells me that mgd over I has to be equal to the angular frequency squared. So I'm going to take that and put that over here. Then I'm going to square root both sides, and we know the angular frequency is equal to 2 pi over period. And just doing my algebra, we end up with T equals 2 pi times the square root of I over mgd, where d is the distance from the center of mass to the pivot point. And again, because I applied the small angle approximation, this equation would only hold true if the physical pendulum was oscillating at small amplitudes.